of surface, and if you just give the chance to that data to just roll down into the into this particular surface, then what happens that if this is basically, if this is correctly, if the features of the EEG signals, if the features of the EEG signals during the inhalation of the unknown stimulus, which is naphthalene, which is known to you only, not the human person or not the subjects. So basically, whenever during the process of inhalation of naphthalene, whatever be the EEG signals are going to be collected, if correct features are going to be, have been extracted or selected, then automatically that unknown data, is going to roll down in near the optima of the naphthalene minima, right? So basically, whenever your minima of the naphthalene, let's say if I say that this is the minima of naphthalene, then automatically if you roll down, then it can go like this, it can go like this, because this is the minima of belief. So if your classifier is correctly designed, if you have right extracted and selected EEG features, if your brain signals are correctly, acquired, then obviously that data should not come to the minimum of belief, because that data obviously, belongs to the naphthalene class. So it will go on this way, right? Go on this way to find out the minima of the naphthalene class itself. And whenever it finds the minima of the naphthalene class, it will, reside, or it is getting its stability. It is going to be stable at this particular, near this particular region. So now you are going to determine, whenever after the equilibrium of your unknown data, then you are going to determine the nearest minimum, nearest optimum of that particular data point, right, on this particular surface. That now whenever your data is going to be, stable, then what, optimum, falls the within the nearest location or nearest, distance from that particular unknown data points, whatever be the, nearest, optimum, you know you are going to be found, then that the class of that particular nearest optimum is going to be, the class of unknown stimulus. And now you come to the, result of the classifier, and now you compare that whether your classifier has been, classifying this particular, data points, the particular, unknown input correctly or not. If the classifier, correctly classify, then obviously you should go on, and you have done, a kind of, robust, you have gone a little bit, a little step closer to design a robust classifier. If there is a misclassification, you should be aware, you know even after performing certain, experimental schedule like that, so that you can get to know that whether there, in the designing formation, whether you have done something wrong or like that. So this is the basic idea of olfactory stimuli classification for this given problem. Now, I have just mentioned in the previous slide that I need to take, a particular function, which function we need to, minimize, and we did, minimize. Why? Because I need to, get it done by some kind of, evolutionary technique, so that it can easily, optimally find out solution for me. I'm not going to, find out the solution by, calculating, through pen and paper, because there lies the beauty of artificial intelligence, right? So basically, I need to select one function, and that function is the Rastrigian function here. This is a function which is associated with evolutionary algorithm techniques. So basically, this is the Rastrigian function. This function looks like this. And you can see that this function has a beauty to contain multiple minima, and it looks like at the Lyapunov surface. And on this Lyapunov surface, basically, we are going to, this surface is going to be treated as the surface of the neural network which we are going to be which are going to design. And what are these, these pockets? These pockets I can take that this pocket are the optima or the minima of that particular, of a particular smell class. So if I take one, pocket like that, I can take that this is the of first smell class, let's say naphthalene. If I take, if I take another, pocket like this, I can consider this as a minima of the next smell class, that is smell class 2, that is, clove, let's say. I can choose many more from this surface, right? Because this surface has several, this kind of, minima. So if I take, even if, 10 classes, then also I can fit in this particular Rastrojin function, surface. And using now Lyapunov stability, now we have designed, a neural network classifier. This is a plot of a two-dimensional, function. If you can go on, plotting the Rastrojin function using MATLAB, you can see, n-dimensional function as well. Now, so after doing this, so what we should, do now? Now we are going to, taking the substance, the object, like the smell object, like naphthalene, and the aromatic features of this naphthalene as the input to this neural network, right? This is our feature vector, what you can see, you have seen in the slide of the pattern classifier slide, right? So this is your feature vector, and this is your, basically the aromatic features are going to be, fed into the neural network as an input. And now we determine the convergence of the neural net to one of the local minima. And whatever be the closest local minima of a particular smell class, we basically denote that this particular, is going to be, belong to that particular class. So basically, whenever we are having the training session, for the training session, we are basically feeding these neural net with each one of input, and we are just observing that whether the all the inputs are, which are basically belonging to one particular smell class, they are heading to one particular local minima or not. Those are the first set of features, that is those first set of features which you can say that which, pointed out the class level of one for the naphthalene class. Then again, we take the second set of input features for, let's say, the second smell class, that is the clove. And we just feed those aromatic features of clove as an input to the neural net, and we just observe that whether this convergence happening to the neural net to another local minima, which basically representing that clove class, the minima of clove class, right? So this is the the approach we designed, for this kind of, olfactory perception, where you can take, a number of, smell stimulus, and you can do your experiment like this. So this is the neuronal dynamics which I am talking about for olfactory perception, that I can, design this particular Lyapunov surface, and these are the, minima. And you can see this is the unknown data points which is coming into one minima. This is the unknown data point which belongs to the next class, which belongs to the, second class here. So it is coming to the, nearest region of the, you know, second minima or second optima, I can say, for second smell class, that is smell 2. So you can have this kind of situation that sometimes the, the unknown data points exactly locating, on the top of the, minima, I mean local minima of a particular smell class. Or else sometimes you may happen, you may find that there is, residing, at a particular small distance, right, from a particular, local minima, which representing a particular smell class. So now you need to calculate that what is the shortest distance. What is the shortest distance? You can see that for this blue, data, which is probably the data points, unknown data points, belong to smell class 1. This is having the nearest, sorry, this is having the nearest, distance with the local minima of smell 1. And it is having, the possibly the far from whatever be the local minima or optima for smell 2 or smell 3, like that. So this is the whole idea, that you should, take into consideration any function which looks like this Lyapunov energy surface. You need to minimize those function, for obviously, by optimally. So I have selected here evolutionary algorithm for doing this thing, which basically, has the ability to give you the optimal solution accurately, and obviously to find out that feature vector, that weight vector, basically, so that the neural net dynamics will settle down to one of several minima, and probably, the settle down correctly. That is the main important point. Now, this is the experimental framework. You can see that this is the experimental framework which we have here. That is, we have taken the 14 channel wireless emotive EEG acquisition system, what I have just, told you, that we, did not take the standalone machine what we had taken for the, previous experiment of previous problem. So this is the wireless EEG emotive headset, which is basically, tied, and which is basically, placed on above the head. And here we consider number of stimuli, 10 intergener, 5 intragener, so that we don't get any kind of, biasness for, generic problems. So here number of subjects we have taken 25, and EEG instances or stimulus, I can say, how many instances we are taking, we have taken for this experiment, that is 250, right? Because this is the, EEG headset, you can see. And because we, every time we are saying that for this brain computer interfacing problem, or for any kind of, pattern classification problem, for any kind of artificial intelligence problem, we should take, the number of instances, a little bit larger, but not very larger, so that the redundancy should come. But obviously, a fairly large number of data sets, so that there is no such kind of, biasness, or no such kind of, misclassification, the, possibility of misclassification, uh, so that this particular possibility is going to be avoided. So this is the experimental framework, and you can see that these are the, frequency spectrum, which you could see if you do the filtering, by designing a bandpass filter and having a, frequency band which is having the 3 to 13 hertz. And this is a kind of, you can see here that what I have just, I have just telling what I was just telling, that features are the, or some eminent speakers have also told previously, that features are exactly this thing which basically, separates a particular object from another. This feature is something like that, right? Feature is that attribute of a particular, object. So here we have this kind of, four smell stimulus, and you can see that these are the, discriminating features. So if I, take into consideration the bandpass filter output between these 3 to 13 hertz, you can see that we are getting some discriminating feature values. That is what I was saying whenever I was explaining the pattern classifier, that particular slide, that we should have a kind of, feature values that should be different, that should be distinct, if we change the object, if we change the input class, right? So that is why you can see here we can have the discriminating feature values if we go on changing the smell stimulus, if we go on changing from odonil to cinnamon, or male perfume, or naphthalene. After that, obviously, we need to choose the right features. We have taken into consideration two EEG features extraction techniques. I have told you in the previous session as well. We have a list of EEG features, and there are all the features you can get from literature review. That is, we have handful of EEG feature extraction techniques. So here we have considered the power spectral density and also the wavelet coefficient features, which proves to be the some kind of distinct feature extract techniques, where we are going to find out some significant feature values, which basically mm, uh, which basically helps to identify or to segregate between the similar kind of generic smell stimulus. See, if you closely look at the indexing of this particular graphical plot, you can see that we have taken some Indian spices, all other Indian spices, right? So cumin, bay leaves, coriander, cardamom, cinnamon, so that inside the similar genre, you can have a right measure to identify right features, and obviously design a perfect classifier, so that you can see that whether the classifier is able to segregate those you know smell or not. So this is all about the obtaining selected features by differential evolution. I have just said that the we are taking into consideration the evolutionary algorithm approach to basically select features optimally. We are not going to select those. We are not going to have the manual feature selection technique. So this is the feature selection technique that we need to define one function, obviously. If we want to have a particular, if we have seen that we have a large number of data points, then, and which probably give me, this is a trial and error process, right? Which probably give me not very fair classification accuracy, not very correct classification result, then I can opt for a data point reduction technique as well, so that I can have a handful number of training instances, handful number of features. And obviously this feature selection is established here by minimizing this particular function and get selected features, which is having smaller dimension from what we have extracted through power spectral density and differential evolution. So if you can see here that before feature selection, the total number of features we have got, that is 272. And whenever we, you know, you know, give that particular task for optimal selection through this differential evolution, then differential evolution optimally selects a handful of 30 features. So these 30 features, mind it, these 30 features are the most significant features for each and every class that can point, a particular stimulus to a particular, class correctly, you know, I can say the with best possible, efforts. So this is a kind of result we can get, that since we have tasted so far with all type of combination of olfactory stimulus, but what happened if I tamper this particular authentic smell of a particular smell stimulus? Can my classifier identify then also? So this is what an experiment we have done, that if I a particular add a particular kind of synthesis like a vinegar solution, like a rose water solution, to a particular smell stimulus, my original smell stimulus. So we have taken three to four, four here, the ultimately the perfume, ultimately the smell stimulus you can see. And we have synthesized all the smell stimulus with three kinds of, this kind of synthesis, artificial synthesis, so that we can temper a little bit about the I mean, authentic aroma of those smell stimulus. And then also I have a particular graph that how much, noise I can add to that particular stimulus, and up to what level of, incorporation of noise can be handled by my classifier, so that I can, I can allow a particular percentage of shift at this particular percent of shift up to that manner in optimum in the Lyapunov of surface, I can say. So this is a result, this is a kind of, experiment I have performed, and we have got a kind of, results, that this kind of, percentage of noise I can added. And even if, 10 to 12, 15% of, noise incorporation, still it is basically, heading to its, correct optimum. And this is a kind of, relative performance of classifiers. So basically, if you can go for any kind of classifier, and with this kind of, this kind of, problems, if you ever want to, work in this domain, then I have given you a handful of, comparison. That is, if you go on these kind of classifiers, all the classifiers you can find in literature survey, then you can see that which classifier has which kind of, what kind of, advantages or disadvantages in performing this kind of, real time problem. And if you can see that here is VM, or, recurrent neural network type, classifier which we have designed, these are having, smaller training time, recognition accuracy is good, recognition complexity is small. So in that very case, we have found, after performing, such kind of, vivid, detailed, comparison with the existing classifier, with the standard classifiers, we have found that these are the, classifiers which can, deal with, talk about. And then obviously I am going to conclude. Yes, it's already, already 11:30, right. So this is the last thing which I would like to show you, that this is the perceptual ability detection of tea tasting, that I have talked to you about the three variants of the three variants. So these are the, whenever we have tasted so much, by taking all the different kinds of combinations of aroma, all the different kinds of, within genre, intra-genre, inter-genre, within genre, outside genre, every time. So now we are very much able to take into, this kind of, variety of three kinds of tea leaves. These are the three kinds of, tea leaves. And whenever we have done this kind of, perceptual ability detection, and if I have extracted the power spectral density features, and if I am going to plot only the 10 features, only by taking the 10, 10 data points, about the 10 data points by taking two feature vectors, then I can see that these are the kind of, clusters you can make for three different variants of tea leaves. So there lies the perceptual ability detection in tea testing, and this basically has been done on, a number of tea testers, and there we have found, the kind of, perceptual ability metric, in the, for the tea testers, and we are going to rank them, and we are going to select the out of, top two or top three tea testers based on their perceptual ability. So this is all about. Thank you, and I'm going to stop sharing my presentation. And I have, I'm going to, give you, okay, so I'm going to give you, the uh, email details, so that you can send me any queries. If you have any queries, then you can send me here.
And please type your email ID in the message box, please. Yeah. So, dear participants, I can see that another man has posted his email ID in the message box. So, whatever, you can ask your personal queries to the email. And still, is there any queries the participants are requested to ask through microphone? Participants, you are requested to ask any queries through microphone.
Good morning, ma'am. This is Rebecca again, once again.
Good morning. Good
Ma'am,
morning.
you have used the BCI device as emotive, right? So,
Right.
when we are using when we're getting the infographic, the machine learning infographic details of the graphs which you have shown. So, how
Yes.
did you derive that infographic details or the statistic infographics?
This is like that whenever you are dealing with this kind of problems, then you are also getting some kind of brain images, right? Some kind of brain images during the continuous process of evaluation. During the continuous of 30 seconds time, you are getting this kind of brain images as well as the signal recording, directly from this emotive session, or from any other standalone
Yeah,
piece.
ma'am, I understand that because I use the NeuroSky headset. So I
Okay.
understand how do you get the brain signals. But my concern is which software has been used for the infographic or some like how you have derived the infographics using some, because when I was working, I was using MATLAB. So I just want to know emotive supports.
Yes, emotive also supports MATLAB, and from there also you can apply those independent component analysis techniques and everything. What you can do in the using that neuroscan, whatever you are suggesting, the same thing are compatible with this emotive headset as well.
Okay, ma'am. Okay, thank you, ma'am.
Okay, so ma'am, I will request you to you can put your email or you can just write down the query and directly email to Dr. Unaga Saha. Then it will help her to answer more difficult. Okay. Okay. So any other participants do you have any queries? Okay. So I think that right now no queries left. So thank you very much, Dr. Unaga Saha, for this valuable session. Again,
Thank you.
we
Thank
wish
you.
that
Thank you,
very
doctor.
connect. Thank you. Thank you all the